Hello, fellow students. Today, we are going to determine the magnetic field around the wire using 4 different approaches. So first, we are going to set up our problem. We are going to have an idealized wire with an infinite length. In real life, you probably wouldn't get an infinitely long wire, but if your wire is reasonably long and you are looking relatively close at it, then you can use this approximation. And also we are going to have a constant current inside. This will work for most cases for direct current. If you have an alternating current, then that's another story. And also we have a thickness of 0 to simplify our problem. So we only consider the magnetic field outside and it has no inside. And also we can determine the direction of a magnetic field by the right hand rule. What we are going to do is basically point your thumb in the direction of the current. In this case, it's to the right. And then curl your 4 fingers. Your finger will be the direction of the magnetic field. So if you do that, you will find that behind the wire, the magnetic field points up, and above the wire, it goes straightly out of the page. In front of the wire, it goes down, and below the wire, it goes into the page. And the first approach we're going to do is the Ampere's law. Because this problem has many symmetries, it's the most straightforward law to use. It's very easy. Write out, it look like this. This B is the magnetic field. Don't ask me why it's B, not M. There's no reason, it's just B. And this dl is the infinitesimal displacement around an arbitrary closed loop you choose. This mu0 is the permeability of free space. It's basically a scale factor. It makes the unit on both sides of the equation right and also scale the magnetic field down, so the magnetic field strength is relatively low. And obviously the I is the current. So this law basically tells you if you construct an arbitrary closed loop around the wire and then you do the dot product of the magnetic field with it, every point on the loop, and then you add all this thing up doing an integral, the result will be proportional to whatever the current you have enclosed in this loop. Now we are going to consider a point distance r away from the wire, so this point here, and we can see because this point we choose is above the curve, is above the wire, using the right hand rule, the magnetic field will come straight out of the page. And by the symmetry, the magnetic field is constant along the circular loop. Because you consider, if you just rotate this point, say to a position at here, then it basically has no difference to a position here. It's both a distance of r from the wire because it's a circular loop, and in nature it doesn't have a preferred direction. Whether you measure the magnetic field from the east or the south or any angle along this loop, it should still be the same magnitude. And also this dl is tangent to the circle. Because it's a displacement, it should always be tangent to the path. And we can choose its direction to be the same as b. This is just an arbitrary direction. We can choose it either into or out of the page. For simplicity, we will just choose it to be out of the page, to be the same direction as the magnetic field. And now we can do the integral to find the magnetic field. First, the dot product, if you recall, is just the magnitude of 2 vectors times the cosine of the angle between them. In our case, it's easy because they are in the same direction. The angle is 0, and the cosine of 0 is just 1. And next, because the magnetic field is constant, we can just take it out of the integral and also consider the magnitude only, so we don't have to bold it. It's no longer a vector now. And next, we just do the integral. This integral is very easy. It just means you add up the length around the closed loop. In our case, it's a circle, so it's just the circumference, which is 2 pi times the radius. And for the magnetic field, we just divide this 2 pi r over, and we found its expression is this. Now it's just a magnetic field strength, it's just a scalar, but we can find its direction by using the right hand rule. And what we can observe from this formula is the magnetic field forms circular loops around the wire. And if you take the direction of the current to be out of the page, you will see it's anti-clockwise. and the strength of the magnetic field is inversely proportional to the distance. So if you increase the r, the magnetic field strength will decrease. The next law we are going to use is Ampere-Maxwell's law. It says the curl of the magnetic field is equal to the permeability of free space times the current density J, and plus these terms, which involves a time derivative of the electric field, and multiplied by the permittivity of free space. This term is also called the displacement current, and is the Maxwell's contribution to this law. But in order to use this law, we have to make some modifications to our original problem. Because if you recall, we said previously that the wire has a thickness of 0. So actually, if you calculate its current density, it will be infinite. But we don't want to deal with the infinite. So in our case, we will view it as a cylinder with a radius r. So the current density will be the original current I divided by the pi r squared, which is the cross-sectional area of this cylinder. We can do it in this way because this current is wire is infinitely long, and we can just expand it, make it thicker. From the symmetry, if you just look at this point and measure the magnetic field, you actually can't determine whether this magnetic field is due to a thin wire or a thick cylinder if they have the same current in it. And also, this current density is a vector. Its direction is in the direction of the original current. In our case, it's to the right. We define it to be the positive k direction in our cylindrical coordinate, with the rho unit vector, the radial one, pointing down, and the theta angle vector pointing into the page. This forms a right-handed system. So if you do a cross product between the rho and the theta, you will get this k. And furthermore, as this current is constant, there will be no time varying electric field. So this term is 0, and this whole equation will reduce to this form. The second term on the right hand side is gone. And this is actually the differential form of Ampere's law we have seen before. You can use Stokes' theorem to convert it into this case, but we won't do it in this video. Now this curl operator in cylindrical coordinate is this. It looks very different to Cartesian coordinate because you don't have this rho theta and this 1 over rho and this rho b theta component. This curl or divergence or gradient, basically this inverted triangle del or nebula, is very different in every coordinate system. You need to make sure you search up the right form of it before you use it. But anyway, in cylindrical coordinate, it looks like this. It may look intimidating, but it's actually not. Because our current density is only in the k direction, we can ignore the first two determinants. What does this mean is we don't care about these two, we only care about this one, and we just find a sub-determinant. You cross out this row, and you only look at this 2 times 2 sub-matrix. And this determinant is very easy. You multiply these two together, and minus the product of these two. So we get the partial derivative of rho times b of theta with respect to rho minus partial b rho partial theta. And don't forget you have a 1 over rho factor in front. As we know, the magnetic field will form circular loops. This is determined in experimental facts. B should only have angular components, so it should not have any components that is going out or going into the cylinder. It should only circulate it. Its radial component will be 0. So this term will be 0, and you only left with this. So you have this. Thanks to our symmetry, the left hand side will reduce down to this, and the right hand side, if you just use our definition of the current density, is basically this. And then we just reduce it to the normal scalar equation. We don't need to care about this k vector here. This gives us a simple differential equation to solve. Because from the circular symmetry and the fact that the cylinder is infinitely long, b theta should only depend on rho. The partial derivative is the same as a normal derivative. We can just write it as dd rho. And then we just separate the variable times this rho to the other side, and we get this. If you wonder why, the b theta should only depend on rho, you can just think that if you rotate the cylindrical wire in any direction, it should still look the same. So it shouldn't depend on theta. And because it's infinitely long, any contribution from up the wire and down the wire will exactly cancel out. So it shouldn't depend on the k, the z direction. It will only depend on the distance away you are from the wire. Anyway, to solve this differential equation is very easy because the right hand side is some function of the independent variable, and the left hand side is just the derivative. We'll just integrate it from 0 to r because our cylinder has a radius of r. In this way, you can cancel out this derivative using the fundamental theorem of calculus. This derivative just gone, and you just substitute the lower and upper limit in it. With the right hand side, this integral is very easy because this whole thing is just a constant. You move it out of the integral. And for the integral of a single rho, you use a power rule. It's just a rho squared over 2. This one is same as a rho to the power of 1. You add 1 to the power, and then you also divide it. Substituting the limits is very easy. Upper limits, you just replace all rho with r, and lower limits, the rho is 0, so the whole thing is 0. Right hand side is the same thing. And also you can cancel out this 2r squared and get this. To find the magnitude, you just divide this r in the left hand side over, and you will find this mu 0I divided by 2 pi r. This is the same result from our last approach. Of course, it should be the same. It's just the same law written out in different forms. And then we can plug in this theta component of the magnitude with the theta unit vector to get our full vector equation of the magnitude. This just tells us the magnitude is anticlockwise in the theta direction. The next approach we're going to use is the Biot-Savart Law. This one looks pretty intimidating, but actually is good for complex scenarios where your problem don't have much symmetries. This law can let you calculate basically the magnitude from anything at anywhere, as long as the current is constant. And back to our thin wire, we want to use cylinder in this time. This time the dl is the infinitesimal displacement over the wire. So it's over this conductor here, it's not along this loop. R prime is the precision vector pointing from dl to observation point. So if your dl is here and your observation point is here where you calculate your magnetic field, your r prime will point from here to here. And still considering a point distance r from the wire, notice that this r is not the same as this r prime here. This r is a constant, but this r prime is a variable. As dl goes along the wire from a length l away, this r prime will get longer and longer. And also we can form a right angle triangle for these three. And for the cross product, if you recall, the magnitude is the same as the magnitude of the corresponding vectors times the sine of the angle between them. Is this angle theta. And also we can notice that because this is a straight line, this phi here inside the triangle is a supplementary angle of the theta. You just use pi or 180 degrees minus this theta and you will get this phi. And from a well-known trig identity, sine of pi minus theta is the same as the sine of theta. So this sine of theta will just be the same as sine of phi. So we keep working. We recall that the definition of the sine in a right angle triangle is the opposite side over the hypotenuse. So it's r over r prime. And r prime from our Pythagoras theorem, we can find it by taking the square of r and l and add them together, then take the square root. Now we are going to find the magnetic field. We know the cross product's magnitude is this one, and we won't care about the direction because we can always find the direction of magnetic field here by using the right hand rule. From this equation, you can immediately see that the r prime on the numerator cancels out with 1 of the r prime cubed on the denominator. And we will get r prime squared here. But from the sine of phi term, we will get another r over r prime. So in total, you still have r prime cubed on the denominator. And we can remind ourselves that r prime is just this thing squared plus this thing squared, add them up and take the square root. Also, don't forget to cube it. Now we just do the integral. The limit of the integral will be from negative infinity to positive infinity. Because this wire is infinitely long, you need to integrate from all over the negative infinity here to all the way there. And this is a pretty standard integral. It's square root things. If you are physics students and you are very lazy, you can just find it online using an integral table or Wolfram Alpha or whatever application you want to use. And the result will be 2 over r squared. And you substitute this thing in, you cancel out with 1 r on the top, and the 2 on the top also cancels out with the 4 partially, and this will give you the result of mu naught I over 2 pi r, the same as before. And for those of you who are interested in doing integrals, I can actually show you how to do this integral. But if you're not interested, you can just skip this part. If we encounter this integral, the first thing we see is the square root, which is disguised in this form of half power. But we want to get rid of it because an integral square root is very difficult to handle. And if we examine the integrand, it has a constant squared plus a variable squared. This L is a variable and R is a constant. I color it in blue for you. Now, if you see two things squared plus together, and you also see a square root or no square root, you should definitely think of the trig sub, as it can make two squared into one thing squared. So the trig sub formula basically comes from this Pythagorean identity. Sine squared plus cosine squared is 1. You should definitely remember this. This is one of the most important formula trig identity for physics. Now we cannot straight use this identity because yes, the squared things are both variables, but in our case one is a constant. So what we are going to do is we just divide both sides by cos squared and get this, and sine over cos is 10 and 1 over cos is sec. Now we get our case at least closer because I have one variable squared and one constant. Then we multiply both sides by r squared to get it even closer. So r squared tan squared x plus r squared equals r squared sec squared x. And now what we're going to do is we let L equals tan x, and if we square it, you find L squared is r squared tan squared x, and then when you plus an r squared to it, you find it's this thing plus this thing, which is this thing. Now you successfully simplify two terms into one terms. And don't forget, you also need to find the differential. This dl here, you need to transfer it to dx. What you're going to do is basically you take the derivative on both sides with respect to x. So the derivative of tan is sec squared. And then you also need to change the limits of integration. When L is positive infinity, x will be pi over 2, as it's r tan x, and this r basically doesn't matter. And if you think of it, tan pi over 2 is positive infinity. So when x is pi over 2, you give your L is positive infinity. The same thing is true for the other bound. When L is negative infinity, x is negative pi over 2. So now you basically done all the trig sub things you need to do. Now what you need to do is just substituting everything into your original integral. Now you substitute in, dl is this thing, and r squared plus l squared all simplifies to this thing. And your bounds of integration also changes. Now for the denominator, it's very nice because you have two things squared here, and you have a half power square root, so you can basically cancel these two here. But you also need to cube it afterwards, so you get r cubed times sec cubed of x. Then you cancel out one of the r from the numerator and also two of the secs. So you get dx just alone in the numerator, and on the denominator you have this thing. But if you remember, 1 over sec is the same as cosine of x, and you can take this constant r out. Now you just integrate cosine, which is very easy because the integral of cosine is just sine. And all you need to do now is substituting the bounds. The upper bound, sine of pi over 2 is 1, is just at the top of the unit circle. And minus the lower bound, sine of minus 2 pi over 2 is negative 1. So 1 minus negative 1 is 1 plus 1, which is 2 over r squared. And now you just plug this whole integral into your magnetic field expression with this a bunch of constant in front. And with doing a trig sub, change it into x, and manage to do this integral, came out to be 2 over r squared. This 2 and this 4 becomes a half, and this r over r squared becomes a 1 over r. So we get this, the standard result of the magnetic field around the long straight wire. Finally, we use the Lorentz transformation to find the magnetic field. So our Lorentz transformation for electromagnetic field is here. The gamma is the usual Lorentz factor, and obviously c is the speed of light, and v is the relative velocity between two frames. This primed frame, like E prime and B prime, is moving, and this unprimed frame S here is not moving. It's in our original lab stationary frame. In the original stationary frame S, a magnetic field will be observed because there's a current here. Now, we can also know that the current, defined as the number of charge passing through a point per unit time, Q over T, can be written as this. We just multiply top and bottom by L, which is multiplied by 1 and doesn't change anything, and it's this, using the definition of the lambda being the linear charge density and the v being the velocity of a single charge. So lambda is number of charge per unit length, and the v is the length traveled per unit time. We can also assume the current is composed from a bunch of positive charges moving to the right, giving this current. Just imagine we are still doing classical physics, and we don't know what's an electron. When you say a current to a classical physicist, they just imagine it's a bunch of positive charges. And therefore, we can move to a frame S prime with a velocity v equals I over lambda. So we will see the charges as stationary. So if we analyze the situation in the stationary frame, the wire is seen with a current and the magnetic field will be produced. The linear charge density is defined as the charge per unit length. In this case, if I put a ruler here and measure length L, and I think, oh, there's 3 charges in there. So if we divide the amount of the charges by the length of this interval, I will find the linear charge density. And if we move in the moving frame, the charges in the wire is seen as stationary, and then electric field will be produced. Now in the stationary frame, there's also electric field because this wire is charged, but we don't care about it. We only care about the magnetic field. But in the moving frame, there's no magnetic field because no charge is moving, only stationary electric field will be produced. And the linear charge density in this frame will be different due to the length contraction, because now we are stationary with respect to the charges. The distance between them will expand into the proper length. So here, if we're using this same interval and closing these 3 charges, we found that this interval actually expand out, so it's longer, but the amount of charge in them is unchanged because charge is conserved. So if we want to find the charge density in this moving frame, we will look at the number of charge in them, which is 3 charges, divided by this expanded length. And from the length contraction formula, the proper length is equal to the contracted length viewed in this stationary frame times the Lorentz factor. And we can move the gamma out of the fraction and see this thing is just the original lambda. So the new lambda is the original lambda divided by gamma. Now to find the electric field, we will consider a cylinder of height h and the radius r enclosing the wire. By Gauss's law, the electric field is a flux which is dotted with the area is proportional to the amount of charge enclosed inside. This dA is an infinitesimal area element on the cylinder with the direction perpendicularly out from the surface. So you can imagine it's a small rectangle here and pointing down. As the wire is infinitely long, the electric field will be purely in the radial direction, so parallel to dA. Because if you look at the electric field here, and you see because say a tiny amount of charge here, you produce an electric field in this direction. But you can also find amount of electric charge here has the same magnitude, producing electric field here. So we have this field and this field, they together cancel out in the direction along the wire, and it only gives you the electric field purely in the radial direction. And because the wire will be the same no matter how you rotate it, it will be constant along the surface, because the surface of the cylinder is the same radius r away from the wire. So we can do the dot product. It will just be the magnitude times together because they are perpendicular, and the E is constant. We can take it out of integral. This is basically the whole surface area, and it's only 2 pi r h. It's basically the area of this rectangular surface of this cylinder. If you expand it out, its height will be h and its length will be this circumference 2 pi r. The top and the bottom cap of the cylinder doesn't matter because the electric field is not in the direction of the wire. There's no flux here. So the right hand side is still the charge enclosed, and left hand side we have just found. Right hand side involves the charge enclosed in the cylinder. It will just be the linear charge density times the height, because it's how it's defined. The linear charge density is just number of charges per unit length. If you multiply by the total amount of length here, you will get the charging here. And you can see that you can basically cancel out the h here and divide this 2 pi r over, and you will get this. The electric field observed in the moving frame is the charge density observed divided by 2 pi r epsilon 0. Now we have the electric field. We just need to transform back to our stationary frame. There's no magnetic field in the moving frame since the charges are stationary. So in our Lorentz transformation, this B prime will just be 0, and we will left out with 1 term. So this is the Lorentz transformation. Since the velocity along the k direction in the direction of the wire moving to the right, and the E we just found or argued is in the radial direction only, they are perpendicular, and their cross product will be maximized, just involve the product of their magnitude. So to know the magnitude, we have this equation. We are not caring about the direction now because we can always find the direction from the right hand rule. And using the electric field from last slide, and recall that 1 over c squared is equal to the permeability of free space times the permittivity of free space. And this relation is basically how Maxwell predicted the existence of electromagnetic waves. He just multiplied these constants of electromagnetism together and found that its value is very close to the reciprocal of the speed of light squared. So this is the speed of light, is the reciprocal squared, and this is the electric field we found from last slide. We can immediately cancel the epsilon 0 here and get this equation. Finally, we have found previous from lump contraction that the contracted charge density is the original charge density divided by the Lorentz factor. And also the current is just the product of the charge density times the velocity of a single charge. Now we substitute everything in. This is the contracted charge density, and the gamma will cancel out, giving us this. And these two things combined together will give us the current. So we have found the standard formula of the magnetic field around the long, straight current carrying wire. And now that's all for today. Thank you guys.